Okie dokie. Let's talk about chapter 3, which is potentials. Potential is a wonderful thing when you think about it. So we're going to start with 3.1, Laplace's equation. So the primary task of electrostatics is to find the electric field for a given charge distribution. That's your whole job all the time. In principle, this is just Coulomb's law, KQ over R squared. And by K, I mean 1 over 4 pi epsilon naught. Okay? Okay? Oh, for God's sake. Unfortunately, integrals of this type are difficult. Okay? So sometimes we can use Gauss's law, and sometimes we get the potential, which is Q over R. And even this integral sometimes is too hard. Moreover, sometimes we don't know rho, and it's difficult, and blah, blah, blah. So some cases, it's more useful to recast the problem in differential form using Poisson's equation, which says that the second gradient or second derivative del squared v is equal to the charge. Okay, so this together with appropriate boundary conditions is equivalent to 3.2, this equation. And very often, in fact, we're interested in a region where the charge is 0. So if the charge is 0, then it doesn't necessarily mean that v is 0. Of course, if rho is 0 everywhere, then v is 0. But sometimes we're looking at a point where we're out here. What's the potential out here? The charge is over here. So there's 0 charge in here, but we want to know what the potential is like here. So we need some reference of what the charge is, but maybe we just need to know what the potential is on the boundary. And if we know the potential on the boundary, then we just need to connect the dots from the boundaries to get our electric and potential fields coming out of it. Okay, so that's our goal here, is to solve Laplace's equation using given boundary conditions. So if we know the potential along this surface and we have another surface over here, then we can just connect between the surfaces and determine the potential everywhere in between them. And so that's our goal by solving del squared v equals 0. And remember, del squared v is just the second derivative of v, dv squared dx squared, and so on. Okay, and that is called Laplace's equation. So Laplace is cool. The solution for these to this equation, these are called harmonic functions because they're sines and cosines and so on, and exponentials. But let's just do the we'll build up to it. Start with the one-dimensional case, go up to the two-dimensional case, which is a little more useful, and then the three-dimensional case. Okay, so suppose your potential depends only on one variable x. You've got symmetries in y and z, so the potential doesn't change in the y or z direction, but it does change in the x direction. Well, it should change according to this, that the second derivative of v with respect to x should equal to 0. The general solution to that is that it decreases in a linear fashion, because dv dx is m, and then dv dx squared is 0, because the second derivative of m, which is a constant, is 0. So that's a line. So that means if you have symmetries in y and z, then your potential will just fall off linearly, okay, as you move from x equals 0 to x equals some other point. And that's what they're showing here. In going in and out of the page, it's constant at this value. Going up or down, it's constant at that value. And then as you go towards x, that's where you have an issue. Okay, so basically what v of x is, what the potential at some point is the average of the potential at, so if you have a point A and a point B, you can calculate the average of the potential here, and that'll tell you the v at point 3 could be the average of 1 and 5 between 2 points, okay? So that's pretty cool. X plus a and x minus a. As long as you know what the a's are, you can determine the potential at any point. Okay, the thing about Laplace's equation is it cannot have any local minima or maximum. It means it has to decrease either as a line or as a whatever or some other thing. The issue is it can't have a little kink in it like that. That's not possible in Laplace's equation, and that is something that electric fields obey too. They don't have little kinks in it. Okay, so let's say we go into 2 dimensions. Then we have this equation. This is no longer an ordinary partial differential equation because we've got x and y. So we've got 2 variables that need to be satisfied in this equation. This is basically what you're trying to look for, is this a continuously decreasing function. No matter what path you take, you're always going down, and there's no little lump here where you can take a rest. You're just falling downhill the whole time. Okay, and that's a 2-dimensional thing. So going through this, I'm about to sneeze, so pardon me while I burst into flames. Here we go. Wow, that was exciting. Felt really good. Okay, so anyway, the thing here, the solutions to these equations, we don't talk about them here yet, but what you care about, what he's talking about here, is that there are no minima or maximum, so as long as we know the boundary conditions, we can specify the solution. Okay, he doesn't talk about the solutions there. Same thing in 3 dimensions. Okay, as long as we can specify the boundary conditions, then we can determine the potential of it. So then here's your proof for something weird, and you got your law of cosines there trying to show this, and he's trying to prove something. Oh, he's got something to prove, Griffiths. All right, so the boundary conditions uniqueness theorem says that if you know the potential on the boundary of a surface, then you can know the potential, the form of the potential all the way through it. So if you know what's going on here and you know what's going on here, you just got to connect the dots, okay? And there's a function that connects them. And that's what the whole point is. If you can figure out the potential at the boundaries, then you can figure out the potential everywhere else. That's kind of a stupid thing because it's like, duh, if I knew this, then of course I know everything inside. But I don't know what this is. Okay, but anyway, this is a really powerful thing because if you can measure the potential along the surface, then you can figure out what the potential is throughout the whole thing, which is actually pretty cool. And there's a couple proofs of that here. So then there's a corollary here. If the potential in a volume is determined, then the value of the boundaries, the potential in a volume is uniquely determined if the charge density throughout the region and the value of V on all the boundaries are specified. So that's, again, pretty cool that if you know some information, you can have all the information. Okay, so conductors here, the second uniqueness theorem says that in a volume surrounded by conductors containing special charge rho, the electric field is uniquely determined if the total charge on each conductor is given, figure 3.6. So as long as we know Q here, Q here, Q here, Q here, and we know some outer boundary or whatever, then if we know the total charge, then we can uniquely determine the electric field. Uniquely, that's uniquely. That's a really important thing, okay? Uniquely, because the main thing about the Laplace's equation is it has infinite solutions. So you can literally make it say anything you want, but you have to, if you know the boundary conditions, then there is a unique solution, and that's our goal, is to find the unique solution so that we don't have to do a bunch of crazy hard integrals. Okay, and then there's another proof of it there, blah, 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 blah. Okay, and then, yeah, that's 3.1. Okay, so that's your main thing, is just to understand that if you know the potential, on something, then you can get the specific case. So we haven't really talked about any solutions yet. We're just talking about, in general, Laplace's equation allows us to determine the potential anywhere. And then if we are in a region where the potential of the charge is known, where the charge isn't zero, then we can use use Poisson's equation, where the second derivative, or the del squared on the potential, is equal to the charge, and then we can get the electric field that way, or the potential. Okay, so that's 3.1.